Thank you for the introduction. Hello, everyone. I'm Esther, and I'm happy to be here today to present a study to you that I've done together with my colleagues Xiaojun and Arno Schlueter from the Chair of Architecture and Building Systems at ETH. And so the study that I want to present to you today took place in this HiLo living lab that you can also see up here. And it's a living lab that during the design phase aimed to integrate energy systems with ultra-lightweight structural components. Now we are in the operational phase of this living lab, and we try to test different building control strategies in real-world settings. The unit has 2 floors. On the lower floor, there are 2 enclosed offices, and the rest of the space is open plan. And here you can see a few pictures of one of the offices downstairs. HiLo is a research space, so we have a lot of sensors there that collect more than 1,500 data points. We also have different heating and cooling systems, and we can turn them on or off depending on what we want and what we need. So in this office where this study took place, we have a ventilation system, we have a hybrid VRF system that was installed by Mitsubishi Electric, and then we have a thermally activated building system, TAPS. And this TAPS system is the most exciting one for us from a research perspective because it is integrated into an ultra-lightweight structural component that you can see here in more detail. This TAPS system, or this floor system where the TAPS system is integrated, consists of a 3D printed floor system that is developed by another research group at ETH, the Block Research Group. And in this 3D printed floor structure, my colleagues Gerrit Leiden and Arno Schlueter integrated the hydronic pipe network of the TAPS, and then there are also EPS insulation blocks as permanent formwork in positions that improve the structural and thermal performance of the floor system. And so we look at this floor system to answer a bigger question, which is how good the energy flexibility potential of this TAPS system is, because it's ultra lightweight, and so we believe that it might actually be quite well positioned to react to grid signals compared to traditional TAPS systems, which are mostly integrated into heavyweight concrete structures. And so to answer this question, we started to develop a data-driven model using the sensor data from HiLo. And here you can see the data set that we got once we downloaded all the data. And then we had 2 options. One was keeping all the features in the data set, but this is of course not recommended because it can lead to problems like overfitting, increased model complexity, and so on. So the way to go is to select only relevant features. And this comes with a few advantages. By selecting only the relevant features, the size of the data set is reduced, which then in turn reduces the computational requirements. Then, then by only having a few features in the data set, the noise in the data set is reduced, and so during the training process, the model can better learn the trends and patterns in the data. And also, if there are just not so many data in the data set, the model is easier to understand and to interpret and to maintain. And so we went for that. We wanted to undertake a feature selection, and the next question that came up was how many outcomes should our model have? And depending on the number of outcomes in the model, there are different methods for feature selection. One is the single target feature selection method, which predicts a single outcome from the input, and then there's multi-target feature selection, which predicts multiple related outcomes from the same input. And so with our model, we want to predict the thermal power of the TAPS to make sure that whatever we do with the TAPS, that it can respond to grid signals and also reduce the energy consumption. But then we also wanted to make sure that the occupants in our living lab still feel comfortable with whatever we do with the tubs. So we also wanted to predict the indoor air temperature of the office. So we had a multi-target problem, and then we looked a bit deeper which methods exist within the multi-target feature selection category, and there are basically two methods. The first one is binary transformation, which converts multi-target problems into multiple single-target ones, and the other one is algorithm adaptation, which adjusts algorithms to handle multi-target problems directly. And so most of the studies we are aware of use binary transformation, so splitting the problem into multiple single-target ones. And we wanted to try out the algorithm adaptation approach because, in contrast to the binary transformation approach, it can preserve and utilize inter-target relationships. So the aim of our study was to compare multi-target feature selection methods to identify the most important sensors in HiLo's sensor network, to then eventually develop a data-driven model that can predict the thermal power of the top system and also the indoor air temperature. And to achieve this aim, we followed kind of a standard methodology to develop a data-driven model. So first of all, we extracted the data from the NEST database and then pre-processed the data. Then we did the feature selection by utilizing built-in algorithms of 3 different machine learning models: a random forest model, a gradient boosting machine model, and a support vector regression model. And then based on that, we developed the models with selected features, and eventually we undertook a few tests and evaluated the accuracy of the model using the root mean squared error. Now I'm already coming to the results. The first thing that we wanted to know which features are important for each of the model. And here on this slide you can see the aggregated normalized weight for the most important features for all of the 3 models, algorithms that we tested. And on the left-hand side, you can see the results for the prediction of the thermal power of the tubs, and on the right-hand side, the results for the indoor air temperature prediction. And you can see 3 very interesting things here. The first one is that there's always one feature that is important for the prediction of one of the targets. So for the prediction of the thermal power of the tubs, the most important feature is the supply water flow rate of the tubs. And the most influential feature for the prediction of the indoor air temperature is the air supply temperature of the ventilation system. Another thing is that can be seen here that when it comes to the prediction of the indoor air temperature, there seem to be more features that are actually important for the prediction than just this one most influential feature. Whereas when it comes to the prediction of the thermal power of the tubs, there seems to be only this one most relevant feature. And then what's also visible here is that the random forest and the gradient boosting machine models, especially when it comes to the prediction of the thermal power of the tubs, there seems to be just really this one variable that is important, but for the support vector regression model, there are more features that are important for the prediction of the target variables. Now we knew that what features are important, and the next question was, okay, how many features do we now need to add to our models? And so we tested different feature counts with the model and increased the features step by step and ran the simulations each time. And so here you can see the RMSE values on the y-axis, on the x-axis the number of features added, and on the left-hand side again for the thermal power of the tubs, on the right-hand side for the indoor air temperature. And what we found out here was that even when first of all, more or less, those RMSE values stay constant regardless of how many features we add, more or less constant. And even when only the top 2 features are added, the RMSE value is below or at least close to the average. So, and also considering that the runtime increases with the addition of more features, we concluded that adding just the 2 most important features is actually sufficient to achieve an acceptable model performance. And then we had a look at the model performance a bit more into detail. And here you can see comparison of the predicted data with just the top 2 features in comparison to the measured data, which is the dashed dark gray line here. And I think the most interesting thing here to see is that the support vector regression model is much better at capturing the peaks, whereas the random forest and gradient boosting machine models, they can't really capture the peaks. And so this is because support vector regression model is much better at capturing specific characteristics in the data, like extreme values, and peaks are extreme values. So the support vector regression model is really good at capturing those peaks. Overall, the model performance is acceptable. What I have to say for those results as well is that we didn't tune the hyperparameters for this study because we just wanted to get a first idea of how the model is performing. And of course, in the next steps, then we tuned the hyperparameters and also tried a few different things to further improve the model performance. This already brings me to my final slide. So first of all, what we learned was that feature selection is really important for developing well-performing data-driven models. We also found a few differences within the algorithms selecting models, features, And the most interesting finding for us was that while this algorithm adaptation method is really well in considering inter-target relationships, this also brings a few challenges because it's really hard to fine-tune and develop the model. Sometimes we added one feature to improve the prediction of one of the target variables, but this at the same time decreased the performance of the other target variable. And so I can imagine that this algorithm adaptation method is good, but the binary transformation method is, I believe, more straightforward and quicker to develop models with. And so this brings me to the end of my presentation. Thanks a lot for listening. If you have any questions, let me know.